SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 22, we will talk about conveyance of water, and this is the part 1 of the lecture. So, the different concepts that we will cover are on modes of conveyance. We will talk about pressure conduit design. Then we will talk about sizing of pipes, and by sizing of pipe we mean both the diameter of the pipe, the grade or the slope of the pipe at which it would be laid, and also the velocity of water in the pipeline. Then to do that, we will learn about different ways or different formulas to do that. So, first we will look into the Darcy-Weisbach and Colebrook-White formula. So, a combination of both is actually used to determine pipe sizes. Then we will look into Chase's and Manning's formula, which are used for open channel flow. And then we will look into pressure conduit design specific formula, which is the Hazen-Williams formula, and then we will solve a problem. So, when we talk about modes of conveyance, as I was discussing in the previous lecture, there could be open channels or there could be pressure conduits. So, in case of open channels, for example, we can have something called flumes, where open channels which is supported above ground using trestles, as you can see in this image, that these are open channels through which water is being transported, and these are raised above ground, and they are because of the profile of that particular area, the topography and all, we may need to design something like that. But usually we do not have open channels for carrying water, which is for actually used for either to a treatment plant or from treatment plant or particularly from treatment plant to the service area. So, sometimes we have got aqueducts, or these are earlier ways to carry water. Now, so closed usually these are closed conduits, but they are made of masonry. So, these are not pipelines. And here the average velocity is around 1 meter per second, and previously this used to be rectangular aqueducts. In olden days we used to construct them, but nowadays if it is constructed, then we go for horseshoe or circular sections for this kind of aqueducts as well. And only in specific cases we will go for this kind of aqueduct design instead of pressure pipes. So, the other is of course pipelines or pressure pipes or pressure conduits. And usually these are pipelines are constructed following the profile of the ground. So, we have discussed this earlier. Why? Because if we can be along with the profile of the ground, then usually we are as close, we want to be close as possible to the hydraulic line. And because if we go below the hydraulic line or above the hydraulic line, there is change in pressure, and we have to take care of that extra pressure either through pumping or by certain other measures. So, the thing is we need to be as aligned as possible with the hydraulic line, or we can say along the ground level as well. So, this is how pressure pipes are designed, but again, as you know, these are pressure pipes. So, we can obviously take them below ground or above ground. So, it does not matter as long as we can provide adequate pressure to transport the water. So, selection of material for pipes, which we will not cover in this particular lecture, but you need to understand that the pipe selection depends on, or the selection of material for a pipe depends on the carrying capacity of the pipe, the pressure that is built up in the pipe, the durability and life of the pipe, maintenance cost and repairs, and many other things. But the pressure is very, very important. That means, pressure plays a big role in the selection of the pipe and determining the thickness of the pipe and the material used and so on. So, when we design pressure conduits or pipelines, we need to understand some basic concept. And first of all, these are closed conduits. So, there is no open surface or anything. So, water flows under pressure which is usually greater than atmospheric pressure, right. And these pipes can go up and down from the hydraulic gradient line, as we were discussing. And even though we desire that it follows the hydraulic gradient line as much as possible, because it leads to economy in terms of the pressure actually is lower in that particular case. Pipes laid lower experience higher pressure, which will influence pipe material specification. And invert level of the conduit is independent of the grade of the hydraulic gradient line. So that means finally when we lay the pipeline, it could, the invert level or the lower level of the pipeline could be at any level. It does not matter, it is independent of the grade of the hydraulic line. So when we look at this particular image, you can see that the pipe is laid where at different points we have got different heights. So over here the pipe is at a higher level, over here the pipe is raised at a lower level, and we are taking water from this side, we are putting water in, and this is where water is going out. So we need to determine the pressure in a pipeline. So to do that, we first have to understand the principle of conservation of energy. So that is based on which we determine the pressure in a pipeline, and we use the Bernoulli's equation. We can write the Bernoulli's equation in different form, but over here we write it in this particular order, where P out is the pressure over here at this particular point, and divided by this gamma represents the specific weight of fluid, which is gamma is equal to rho into g. Rho is density of fluid and g is gravity, right? So acceleration due to gravity. So this P out by gamma plus V square out by 2g plus Z out. Z out is the height. So Z out is the height of the pipeline or the center of the pipeline from the datum. So we can take this particular part of the equation, and we can see that this part is the pressure head, this part is the velocity head, and this part is the elevation head. So in other terms, this is the kinetic energy, and this, when we are talking about conservation of energy, this is the kinetic energy, this is the pressure, and this is the potential energy in the pipeline. Now at every point this is conserved, right? So that means if the overall pressure or the total energy over here at this point and this point, if there is a difference, that means of course over here it may be lower. Why? Because there may be some losses in the pipeline. That means for water to travel from here to here, there would be certain kind of loss of energy in the pipeline, and that loss is because of frictional losses and some other minor losses, because pipe diameter changes. There are many reasons why there is loss of energy in other loss, but you can call it a minor head loss, whereas the major head loss is due to the friction. So we can even ignore this part, right? So loss by G is equal to this head loss due to friction. So we are dividing by G to get the loss. So this, from energy we are actually converting it to the head. So that is how when we if we assume that the velocity would remain same from this point to this point, which is also known as steady state flow, and if I say that the Z value or the height of the pipe, it would also be more or less same, in that case what happens is P out by gamma is equal to P in by gamma, that is the pressure that you are putting in, minus this head loss. So I can even ignore this part. So in that case, this loss due to friction plus pressure in is plus pressure out is equal to pressure in, right? If I just transfer this from here to this side. So P out by gamma plus loss by G or frictional loss, head loss due to friction, is equal to the pressure that we are putting in. So this is actually equated, and this actually leads to the formula of which was finally derived by Darcy-Weisbach, which we will discuss. So this is and this velocity head is basically TEL minus HGL. So TL is the total energy line minus the hydraulic gradient line, right? So this gives us the velocity head as well. So from using this conservation of energy principle and following Bernoulli's equation, we can actually derive the head loss in a particular pipeline. And if I can derive the head loss, from there we can derive the diameter of the pipe, we can derive the slope of the pipe, everything could be derived from that onwards. So when we design a pressure conduit, there could be pipes connected in series, that means one after another. So, in that case the total head loss, that means the frictional loss that happens in the pipeline, is a summation of the head loss in individual pipes. So, whatever frictional losses that we have in a pipeline, that gets added up. Now, if pipes are laid in parallel, for example, we design a basic loop like this. That means water comes like this, it goes around, then it goes around, and then this is the loop. So, in this particular case, pipes are laid in parallel. This sometimes has to be done when we have to lay, there is an old pipe, but we want to increase the supply in this particular area, so we lay a new pipe, or it's like putting in a backup during repairs, or if I want to avoid large diameter pipes, instead we want to give 2 smaller diameter pipes. In this particular case, what happens is pipes laid in parallel will result in same head loss in each pipe. So, because over here at this point and over this point, the head loss would be same in both the pipes, right. So, these are the 2 rules that we can follow eventually when we design networks and all, and that we will discuss again in a later lecture in detail when we actually solve a network design. So, optimum velocity is determined for each pipeline, that we discussed in the last lecture, that for different diameter pipelines we can determine an optimum velocity, so that pipes are neither too large or neither too small. And whenever we are doing pipe design, we need to overcome the frictional loss and other losses due to, and these other losses are minor losses, which is because of due to change in flow geometry, like there is a bend, there is a valve, then there is a reduction in pressure, there is all these different pipe fittings that are put in. So, this could be also considered as the other losses. So, it is not only the frictional loss along the pipeline, but also the other losses because of presence of fixture, presence of a bend, all these things influence losses or head losses in a pipeline. Now, head losses basically means the pressure loss, and that means we have to put, based on the head loss that happens in a pipeline, that amount of head loss plus the final residual pressure that we require has to be put inside that, that kind of pressure has to be provided, either by raising the water to overhead tank so that we get that kind of pressure or that kind of head, or by putting or using a pump which could be able to give that kind of a meter head. So, the total quantity, in addition to this determination of loss of head, we need to understand the total quantity, or in particularly it is measured in cumex, cubic meter per second, or this is the flow actually, and this is based on the population and the projected population, of course. So, because we are designing pipelines not only for today, but for maybe for the next 30 years, then the peak demand periods, or the peak demand and the demand distribution, that how the distribution happens. Now, this is important for operation of pumps and maybe for some other issues as well, but primarily we will design the pipelines for peak demand. So, the first formula that we will learn to determine loss of head in a pipe. So, this is the old 100-year-old formula, and we directly do not use it in transmission or this kind of pipe design problems, but with some more detailed calculations we can use it. But in this particular form that you are seeing in this particular slide, it is difficult to implement that. I will explain that. So, HL is equal to, head loss is equal to F dash into L into V square by 2 G into D. Now, this could be solved. I did not show the detailed calculations, but actually if you take the incoming pressure and the outgoing pressure, and then the difference between that is equals the particular head loss, and we can actually get this particular formula by solving that, right. So, FL V square by 2 GD, where HL is the loss of head in meters, L is length of pipe in meters, D is diameter of pipe in meters, V is mean velocity of flow through pipe in meter per second, G is acceleration due to gravity, and F dash is Darcy's friction factor. Now, instead of Darcy's friction factor, some authors also choose to use Fanning's friction factor, and this is small f, and Darcy's friction factor usually we give right with F dash, and the relationship between these two is F dash is equal to 4 times of F roughly. And sometimes we can take approximate values of F dash like 0.02 for new pipes and 0.07 for old pipes. And if you want to do a little bit more detail, we have other empirical formulas such as 0.02 into 1 plus 1 by 35 d for new pipes, d is diameter, and f dash it could be 0.04 into 1 plus 1 by 35 d for old pipes. So, that is basically either you can directly use this or you can go with a little bit more detailed calculations, but still these are empirical formulas which are derived in certain cases, but it is not universally applied. So, that means until unless we can determine this f dash properly, we cannot determine the head loss in a pipeline. So, f dash is very this is the Darcy's friction factor, and if I want to for urban planners, as long as we know the basic concept, that is fine, but when you are actually an engineer designing a pipeline, you really have to go and do detailed calculations to estimate f dash values. So, how do I determine f dash? So, Darcy's friction factor depends on two things. One is the relative roughness of the pipe or the smoothness of the internals of the surface of the pipe, and the Reynolds number. So, what is Reynolds number? I will come to that. So, these are the two parameters which are important, and there is another criteria. When Reynolds number is less than 2000, we assume that the flow in the pipeline is laminar, which is actually not, and then we say that, well, in most cases it is not, then this f dash equal to 64, we can assume that f dash value is equal to 64 by Reynolds number. And if Reynolds number is greater than 4000, then we can assume it is a turbulent flow inside a pipeline. So, that is usually in the most cases it is a turbulent flow, right. So, that means if Reynolds number is greater than 4000, then we assume it is a turbulent flow, and accordingly we can choose f dash values, which can be estimated, this Darcy's can be estimated for turbulent flow using another equation, which is the Colebrook-White formula. As I was telling you earlier, that is Darcy-Weisbach and Colebrook-White formula together could be used for designing our pipelines. So, but alone Darcy's with those empirical values is better not to use that particular formula. But if I use Darcy's with Colebrook-White, it can be used. Now, Colebrook-White formula is solved for many types of pipes with different kinds of roughness, and then based on that we can generate the and also based on the Reynolds number, we can generate the chart which is called the Moody diagram. Over here you can see this particular chart. This is Reynolds number on the x axis, and on the y axis we have friction factor, and on this side also you can see the relative pipe roughness. For different levels of roughness, like this one, you can see this value, these lines are going like that. You can choose a particular friction factor. That means for certain Reynolds number you can get a particular friction factor. So, this we can directly use the Moody's diagram, or we can use Colebrook-White formula to actually calculate. Now, let us see the Colebrook-White formula. So, this is the Colebrook-White formula, where we can see that 1 by root f, where f is Darcy's friction coefficient, is equal to -2 log to the base 10 into this k by 3.7 d plus 2.51 divided by Re into root f. Now, Re is again Reynolds number, k is the new term which is the roughness. So, I was telling you earlier that it depends both on roughness and Reynolds number. And what is Reynolds number? Reynolds number is fluid density into viscosity. Fluid density in case of water it would be 1. So, we can even ignore that in case of water. So, velocity into diameter of pipeline divided by viscosity. So, viscosity of that fluid, of course. So, these are the different things that actually plays a role in determining Reynolds number and what kind of flow will happen. So, Reynolds number actually determines if it is a turbulent flow or it is a laminar flow. Like you can see that this range is the laminar flow part. This part is a transition zone in between that laminar range 2000 to 4000 part, and beyond 4000 we can call it is definitely a turbulent flow. So, based on this, we can a combination of both of this we can actually use to determine the loss of head in a pipeline. So, but alone Darcy-Weisbach cannot be utilized. So, either you follow Moody's diagram or you can use the formula directly to estimate the Reynolds number, and from there we can calculate. Now, this K value of roughness again could be looked at from charts, and I have provided the chart over here for your reference, where you can see that metallic pipes, cast iron, ductile iron, this kind of pipes, the value for new pipes is around 0.15, and like for PVC and then GRP and other plastic pipes, this is glass reinforced plastic and this is 0.003. And we, for working purpose, design purpose, we also use the same smoothness values. So, roughness values or smoothness values, whatever way you want to call it, doesn't matter, but basically it gets into this both roughness as well as Reynolds number is useful for determining the Darcy's friction factor. So, this together can be used for designing pipelines. Similarly, we can also, we have open channels like flumes or maybe other cases, there we can go for formulas which are specific to open channels, and we have two formulas. One is the Chase's formula for open channels, where Q is equal to A into C into root mi, or we can also have, instead of Q, we can also go for velocity, that is Q is of course the flow, the quantity, and this V is velocity, where V is equal to C into root mi. So, when Q by A is equal to V. Now, A is the area of flow of water, M is the hydraulic mean depth or hydraulic radius. Hydraulic radius is area by perimeter. Hydraulic radius is for a particular pipe is the area of the wetted part of the pipe and the perimeter of the wetted part of the pipe. And I is the slope of the bed, or that means the slope of the pipeline, and C is Chase's constant, and again which we can refer from particular tables. So, Chase's formula is not that commonly used in nowadays, but we have got Manning's formula as well, which is more common, and particularly this is again Manning's formula is an empirical formula, and it is used to estimate the average velocity of a liquid flowing in a open or partially open conduit, like a drain, right. So, usually this is used for open channel flow, and flow variables can be estimated for flow in partially full conduits, like it is a half filled circular pipe or a 2/3 filled circular pipe, and free surface like that of a open channel flow. So, it is similar to the free surface of a open channel flow, because it is partially flowing, that means there is a open surface and there is turbulence in that. So, usually sewage flows inside pipelines, inside sewer lines and all, which sewer designs are such that it is not full, that always there is some amount of space left, right. So, that means we keep the sewer 2/3 full or half full, something like that, and that is where we will use this Manning's formula. So, Manning's formula is very, very appropriate for sewage flow, but in case of pressure pipelines, where more or less the entire channel of the pipe is filled, in that case we usually go for other formulas, or maybe the Darcy and the Colebrook-White combination formula. So, how is Manning's formula given? Manning's formula is HL, head loss, is equal to N square. N is the Manning's roughness coefficient into V square. V square is the velocity of flow through pipe in meter per second, into L. L is the length of pipe in meters, divided by R to the power 4/3. Now, R is basically the hydraulic radius or the hydraulic mean depth of the pipe in meters. Now, R is, as I was telling you, R is equal to A by P, and for circular pipes and also flowing full, it is D by 4, right. So, pi R square, pi D square by 4 divided by 2 pi D by 2. So, that actually comes to D by 4, and this is for circular pipes flowing full, but as I was saying, in sewer design it never flows full. So, we also have to learn about those things later on. But for right now, we leave it at that if R is equal to A by P, or in case of circular pipes, we can also assume D by 4, assuming it is flowing full. So, A is the cross-sectional area of flow normal to the flow direction, and P is the wetted perimeter of the cross-sectional area of flow. Okay. So, this is HL, and this is, we have got V over here, and over here we have got L, and then over at within R 4 by 3, R is the hydraulic mean depth. So, which is where we have got both area and perimeter, right. So, using this we can rewrite the formula in a different way, where we can actually have V instead of HL, and then V becomes, if V goes on the other side, That means V is equal to 1 by n R 2/3 into S to the power half. Now, why S? S is basically the slope of the hydraulic grade line or the linear hydraulic head loss, which is same as the channel bed slope when the water depth is constant. So, S is equal to HL by L. So, HL by L. So, when I bring L to this side, this becomes below HL by L. Now, what is the meaning of this? That means head loss per unit length, right. So, head loss per unit length is basically, we call it the S or we can call it the channel slope, right. So, this is the linear hydraulic head loss, which is same as the channel bed slope. So, V is equal to 1 by n R to the power 2/3 into S to the power half, and R also instead of 4 by 3 becomes, because of the, we have to, if I take V square on this side, we have to take a square root, that is why it becomes 2/3. Okay. Similarly, we can also convert it into Q. If V is there, then we can also determine Q value as well. So, there could be different forms in which this particular equation could be written. So, we can conclude by saying that a channel with a larger hydraulic radius will have a higher flow velocity and also a larger cross sectional area. So, this means the greater the hydraulic radius, larger volume of water it will be able to carry. So, larger hydraulic radius indicates that it has a larger cross sectional area as well as a higher flow velocity. So, finally, we come down to the Hazen-Williams formula. This is again an empirical formula. It has its own issues, I will discuss that, but this is the one which we usually use for pipe designs, and this relates to the flow of water in pipe with physical properties of the pipe and the pressure drop caused by friction. And usually we use it to design pipe sprinkler system, water supply networks, irrigation systems and so on. So, what is the formula? V is equal to 0.85, this is a constant, into CH into R to the power 0.63 into S to the power 0.54. Now, Q is and so what is CH? CH is the coefficient of hydraulic capacity. This is the constant that we have to determine. Then R is the hydraulic mean depth of the pipe in meters. V is velocity of flow through pipe in meter per second. S is the slope of the hydraulic grade line that we have discussed last time as well, and D is the diameter of pipe in millimeters. And we can also rewrite the formula in different ways, and for particularly for circular conduits, if I take the value of R, the hydraulic mean radius, and I change it to D by 4, in that case we get this equation where V is equal to 4.567 into 10 to the power minus 3 into CH into D to the power 0.63 and S to the power 0.54. Now, if we have V, we can also convert it into Q, because V by A is Q, because we can determine A as well, and then what happens is we can get 1.292 into 10 to the power minus 5 CH into D to the power 2.63 into S to the power 0.54. So, this is how we can write the formula in both ways, either using V, or we can determine, if we know V, then we can determine others, or if we know all these values, then we can determine V, and similarly we can determine Q as well. So, Q is basically the discharge in cubic meter per hour. So, the issue with this formula is the numerical constant of Hazen-Williams formula, which is 0.85, as I was showing you earlier. This is in MKS units and 1.318 is in FPS units, but this is calculated by assuming a hydraulic radius of 1 foot and friction slope of 1 by 1000. So, this is something which is fixed, and based on that we have arrived at this 0.85 value. But this formula is used for all ranges of diameter and different friction slopes, right. So, the slope value, the friction slope value that we are using in this particular formula, this is more or less same for, in every cases we are assuming 0.85, but actually it is not. So, this may result in an error of up to plus minus 30% in the evaluation of velocity and plus minus 55% in the estimation of frictional resistance or head loss. So, you can understand the implications. So, if I use this formula, there may be a chance I can end up with 30% higher velocity in the pipeline, and that will again lead down to if I consider that, then the diameter has to be adjusted, and that actually will lead to lot of maybe increase in the cost of the pipelines. And same is 58% increase in the frictional resistance. So anyway, so we can still use this formula. We will see that by solving a problem, and for this Hazen-Williams constant, that CH value, this is the chart that is has been estimated or calculated, and this you can see that for cast iron or ductile iron we usually go for 130 for new pipes and 100 for design purpose we can take 100, for mild steel pipes 140 and 100, and similarly we can go for this non-metallic pipes like PVC, glass reinforced plastic and other plastic pipes 150 and 145 and so on. So usually these tables are for reference. You can just refer to those whenever you choose a certain kind of pipeline, and you can use those CH values. So let us look at a problem. Water has to be supplied to a large city with a population of around 6,25,273 people. The daily water consumption is at the rate of 220 liters per capita per day. So this is the basic info that you have got. Now you have to estimate the size of supply conduits leading to the service area where flow velocity is 1.4 meter per second. So we assume that the flow velocity is 1.4 meter per second, which may be appropriate for this particular case. So find the hydraulic gradients at which pipelines are proposed to be laid using Hazen-Williams formula. So we are specifying that Hazen-Williams formula has to be used, and everything else you can assume. So Hazen-Williams formula, this is the formula. We will use V equal to 0.85 into CH r to the power 0.63 into S to the power 0.54, where S is the slope, CH is the coefficient of hydraulic capacity. This is the friction slope, that is change of friction per length of pipeline. Then V is velocity of flow through the pipe in meter per second, and R is the hydraulic mean depth of the pipe. So in this particular case, you can see that when we solve the problem, first we determine the diameter of the pipeline. How we did determine that? So first of all, the quantity of water required is 220 liters per capita per day into the population over here. So this will give us 132 million liters per day. So maximum, now the thing is, this is the average demand. So as we have said that the pipeline has to be designed for maximum demand or peak demand. So either we can use, if it's a main line, we can go for 3 times that particular value, or if it's not a main line, then we can go with 1.8 or 2 times that value. So over here we have used 1.8 times. So assuming maximum daily demand is equal to 1.8 times the average daily demand, which actually we have to multiply this 130, sorry, this would be 137, not 132. 137 for 5.6 million liters per day into 1.8, which comes to 247.6 million liters per day. So this is the value that is required. This is the amount of water that has to be supplied per day. So the maximum design capacity will be, this water has to be supplied in the 24-hour period. So as I told you that earlier, we have discussed that Q value is equal to, is measured in Qmix. Qmix is cubic meter per second. So 247.6 million liters into 10 to the power 6 divided by 10 to the power 3, because it's cubic meter, we are changing liters to meter, and then divided by 24 into 60 into 60, that converts it into per second from per day. So at the end of that, we get around 2.87 Qmix, not Q6, Qmix of water, right? So which is 2.87 meter cube per second of flow that is required in this particular system. So if we know that, Q value, we also have got V value, which is 1.4 meter per second. So from that we can determine the value of A, or the cross section of that particular pipeline. So that comes to around, if I have got A, then Q by V equal to 2.87 by 1.4, it is 2.05 meter square. So D value is equal to, of course, A is pi d square by 4 is equal to 2.05 meter square. So then we solve for D, we get around 1.62 meter. So this is the diameter of the pipeline that we have to choose to supply water at a velocity of 1.4 meter per second for this particular town. So now in the second part, what we have tried to determine what should be the slope of the pipe that should be laid for this particular main. So, we now have this Hazen-Williams formula, and now we are putting all the different values. V value we know, CH value we choose 130 for unlined cast iron pipes. Let us assume it is a new pipe. Then R value is equal to D by 4. It is a circular pipe flowing full. So, we get around 1.62, which we determined the diameter of the pipeline last time, divided by 4, which comes to around 0.405. So, now we have to determine the S value. S is the slope or the hydraulic or that friction slope that we have to provide. So, substituting these values, we get that 1.4, we put all the values in the equation and then we solve for it. So, S to the power 0.54 comes to around 1 by 44.59. So, this then again S we take it on the other side, this value, and so 1 divided by 0.54 comes to around 1.85. It goes to the denominator, and when I solve this, we get around 1 by 1124.83, and we can take it as 1125. So, what does it mean? The hydraulic gradient is 1 by 1125. That is, for every 1 meter fall in every 1125 meter length. So, that means 1 meter friction for every 1125 meter of for pipeline length. So, this is the slope at which the pipeline has to be laid. So, to conclude, Manning's formula is appropriate for open or partially open conduits and not suitable for pressure conduit. Darcy-Weisbach formula can be used to design pressure conduits if Darcy's friction factor is estimated using the Colebrook-White formula. And finally, Hazen-Williams formula can lead to large errors in certain cases. So, we have to be careful in using this formula. So, these are the references that you can follow. Thank you.